Here we're going to look at some more shapes of molecules. Now before you watch this video, I suggest you go back and look at the introduction to shapes of molecules because some prior knowledge is going to be required for these ones. Now what we're going to need to do is look at these different examples here where we have some lone pairs of electrons and we need to be able to draw their structures and showing how the lone pairs will actually affect the shapes of these different molecules. Now first of all, what we need to do is look at the types of pairs of electrons that molecules have around their central atoms. So the first thing that we can have is we can have bonding pairs just as we saw in the first video. So here we have two bonding pairs of electrons repelling one another. Now I'll show you what that looks like in a methane molecule. So here we have methane. We have repulsion between this bonding pair and this bonding pair here. So that's why these electrons are going to repel to get as far away from each other as possible. So all around, that's why they form this structure. These electrons are repelling as much as possible so that in the final structure there's minimum amount of repulsion left. So they repel to get as far away. Here we have 109.5 degrees bond angles, so these electrons as far away as they can possibly be, and this final structure has the minimum amount of repulsion. So sometimes we can have structures where the electrons are not all involved in bonding. So we can have repulsion between bonding pairs and lone pairs of electrons. So these are pairs of electrons which haven't been involved in the bonding. So if I show you methane again, let's say that we took this bonded hydrogen away. Here we have one lone pair of electrons on top here, on top of the carbon atom. We have some repulsion between the lone pairs of electrons that we find up here and these bonding pairs. So again we have some repulsion here. Now because these are lone pairs, the repulsion is actually greater than it is between two bonding pairs. So there's more repulsion from these lone pairs. That will have the effect of squishing this molecule down and reducing the bond angles between the bonding pairs. And that is because bonding pair repulsion to lone pair repulsion is greater than bonding pair to bonding pair. We can also have a situation where you have more than one lone pair of electrons. So we may have repulsion between two lone pairs. So we have lone pair repulsion between two lone pairs. Now again, that will have the effect of reducing the size of the angles between the bonding pairs that still exist. So if I remove another hydrogen from the methane molecule, this angle will be reduced even further because we have two lone pairs of electrons here. Now, these lone pairs, so a lone pair here and the lone pair here, are repelling each other the most. So lone pairs repel the most, so they will be the furthest away from one another. Bonding pairs to bonding pairs repel the least. So we have the highest repulsion here between two lone pairs. We have the lowest repulsion here between two bonding pairs. And in the middle we have repulsion between bonding pairs and lone pairs between the two. Let's have a look to see how this actually affects different structures. Now we can do calculations just like we did in the first video in the introduction to shapes of molecules. So in the first example here, we'll have a look at tin. So we've got tin, our central atom, is in group 4 of the periodic table, so it has 4 electrons in the outer shell available for bonding. Bonded to that are 2 chlorine atoms. So you can see here we've got the tin with 4 electrons in the outer shell. We're bonded to 2 chlorines, so chlorine brings 2 electrons available for bonding. Again, if we do our calculation, we can see we have 6 electrons in total. Divide that by 2. That means we have 3 pairs of electrons. Now if we look back at our structure here, this time, unlike in the first examples in the first video, you can see that only 2 bonds are actually formed between the tin and the chlorine. So in this situation we have 3 pairs of electrons, 2 are bonded and 1 lone pair of electrons. So we have a lone pair of electrons and two bonded pairs of electrons in this situation. Now if we have a look at what the structure will actually look like, we have tin here, bonded to two chlorines, and we have a lone pair of electrons on top of the tin, which we represent here with two crosses. So we've got a lone pair of electrons. That means this bond angle is going to be less than it normally would. Now you need to look back at your original structures and compare the number of bonding pairs or the number of pairs of electrons around the central atom. So here we have 1, 2, 3 pairs of electrons. So we compare this to our trigonal planar structure, which has 120 degree bond angles. But I said that this bond angle here is going to be reduced because of the lone pair. Now for a lone pair, what you need to do is take away 2.5 degrees per lone pair. So for this example, which started off, if we compare it back to a trigonal planar molecule, we would need to look back at 120 degree bond angles and take away 2.5 degrees. That leaves us with a bond angle here of 117.5 degrees. So the bond angle here is 117.5 degrees. That would look a little bit like this one. Now you'll see that we have our central atom here, which is tin. We have our two chlorines here. The angle here is going to be reduced down. It's not that obvious that you can see it here, but this angle is 117.5 degrees because of a lone pair of electrons sat here at the top. Now we can call this one of two things. We can call it V-shaped or bent. Have a look at your syllabus. So that's bent. You have a look at your syllabus to see what they'd rather call it, but this is either a V-shaped or bent. So that's having a look at when we've got one lone pair of electrons. What we'll do now is we'll have a look at another example. We'll have a look at ammonia as well. So we're going to follow the same pattern to work this out. So here we have nitrogen as our central atom. Nitrogen is in group 5 of the periodic table, so brings 5 electrons available for bonding. We have 3 hydrogens attached. So we have 8 electrons in total, which gives us 4 pairs. So we have 4 pairs of electrons in total. If we look back at our original structure, we have 3 hydrogens attached to the nitrogen. So that suggests we have 3 bonded pairs and 1 lone pair of electrons. So 3 bonded pairs, 1 lone pair of electrons. Now let's have a look to see what the structure would look like here. So we have our nitrogen as our central atom. We then have 1 hydrogen coming towards you. We have 1 hydrogen going away. And we have 1 hydrogen on the plane of the board. We have the lone pair of electrons on the top here of the nitrogen. So again, these bond angles here are going to be reduced down. Now what we need to do with this one, again, is look for the number of pairs of electrons around the central atom. So we've got 1, 2, 3, 4 pairs of electrons around the nitrogen. If you look back again at your original structures, that means you need to compare it to the tetrahedral structure with 109.5 degree bond angles. Now remember that for every lone pair, you take away 2.5 degrees Celsius. So 109.5 minus 2.5 leaves us with 107 degree bond angles. So the bond angles between these hydrogens here and then round the back to this hydrogen is 107 degrees. So this structure is a pyramid structure and it's called a trigonal pyramid. So trigonal pyramidal. Sorry, I said trigonal pyramid. So this is trigonal pyramidal. So again, you're following exactly the same pattern. It's very, very simple. As long as you learn the original structures, you must learn those original structures. If we have a look at an example of this, if I take the structure of methane, I've removed one of the pairs of electrons. I've removed the hydrogen from the top here. So we have a lone pair on here. This structure does not show the reduced bond angles. But what happens is these bond angles are squished down because of the lone pair here on the top. So that reduces the angle between these bonded pairs, because there's less repulsion between bonded pairs and lone pairs and bonded pairs. Let's look at another example. So we can look at hydrogen sulphide. Here we've got sulfur. And if you have a look again at the periodic table, sulfur is in group 6. So it has 6 pairs of electrons for bonding. There are 2 hydrogens attached. So there are 2 hydrogens attached to it. That gives us a total of 8 electrons. Divide that by 2, 4 pairs of electrons. So if we think about our original structure, we've got 4 pairs of electrons. So that means our original structure we're basing this on is tetrahedral as well. But this time, if we look back, we've got 4 pairs of electrons, only 2 of which are actually involved in bonding. So we have 2 bonded pairs, and we have 2 lone pairs here. Let's have a look and draw the structure and see what that would look like. So we have our sulfur here at the top. Now we have 2 lone pairs of electrons as far away from each other as possible so that the final structure has minimum repulsion between the pairs of electrons. And then again, we have a V-shaped molecule where these are squished down because of these lone pairs of electrons. So this again is V-shaped or bent. Now we were basing this on 4 pairs of electrons, so we're basing this on 109.5 degree bond angles. But we have 2 lone pairs, so this time we take off 2.5 degrees per lone pair, we take off 5 degrees for this bond angle. So 109.5 minus 5 leaves us with 104.5 degree bond angles. And that's your structure for hydrogen sulphide. We'll look at one more structure here, xenon tetrafluoride. So we've got xenon in the middle, which is in group 8 of the periodic table. So a little bit weird here, because obviously we've got a noble gas here, normally not forming molecules, but we're reacting with fluorine. Fluorine's so reactive it would be able to, under the right conditions, react with xenon. So we've got fluorine, there are 4 of them. In total, this gives us 12 electrons. Divide that by 2, that's 6 pairs. So here, if we look at our structure, this time we're going to want to base it on the octahedral structure. So that's this shape. This is the one we're going to actually base it on. Now, it's a little bit more complicated than the other one, and it's sort of knowing the special case as much as anything, but you can work it out by looking at the amount of repulsion in the final structure. So here, we've got 4 pairs of electrons, we have 2 lone pairs of electrons, and we have 4 bonded pairs. So we have 4 bonded and 2 lone. Now, I'm going to draw the structure for you. So we have the xenon, which is our central atom. We have 2 fluorines going into the board, away from you, and we have 2 fluorines towards you here. Our lone pairs of electrons are above and below. So, having a look at the structure, we have a square molecule which is on one flat plane. So we have our lone pairs. We have our lone pairs above and below the plane here. So that's a lone pair and that's a lone pair. This leaves us with 90-degree bond angles in our final structure. So we're not doing the calculation of taking off 2.5 degrees because the lone pairs are above and below here, and this is the final structure with the minimum amount of repulsion. This is called a square planar. Molecule. So this is square planar because it's square shaped and it's on one flat plane. So here's our flat plane. Again, it's square. If we have a look from the top, we can see it is a square and it's got 90-degree bond angles here. Now if you look at this structure, the reason being the final structure has the minimum amount of repulsion. In a future video, I'm going to look at a T-shaped molecule and it will help explain exactly why it would form a structure such as this, rather than anything else. Ultimately, it means we have the minimum amount of repulsion in that final structure, and that's the key thing you're looking for. What we also need to look at for A-level is shapes of molecules and ions. So we need to look at when we have a positive charge or where we have a negative charge on an ion. Please look back at the previous video on introduction to shapes of molecules. And remember to like and subscribe to my future videos. Thank you for watching.